Okay, so today's lecture, if there were 3 or 5 lectures that I thought were, hey, these are the most important ones of the semester. Like when you walk out of this class, this is the stuff that I would want you to know, take with you. Today's would be one of them. Okay, so all these derivative rules, right? We've been for 2 weeks now. All these rules. What exactly are you finding when you're taking the derivative? Talk to the person next to you. What exactly are you finding when you're taking the derivative? Go. All right. Seaver, Stockwell, receiver. Yes, sir. What'd you guys talk about? Right. Okay, good. So you're finding a rate of change function for the original function. Okay? What's that? So yes, it's a rate of change function. How would you describe a rate of change function? What's the meaning of that? Go. What's a rate of change function? Anytime you're asked the question to describe or explain a function, your answer should always have to do with talking about the independent variable and the dependent variable. That's what describes a function. Is that what you talked about? You should have. Anytime someone asks you, what is this function about? It's always about identifying the independent and dependent variable. That's always what it will be about if you're asked to describe a function. Do you want to talk again? Where's Melissa? You're next on the list. Can you tell me what a rate of change function is? Okay. So then what? Okay, that's true about any function. So then what makes it a rate of change function? The rate of change of the dependent variable? So if we have a rate of change function, where does rate of change fit into this? Rasco. Okay, so a geometric interpretation would be it's the slope. Unfortunately, that's pretty. So because we haven't really talked about that in that framed it that way because it's not a really deep meaning, right? So, so the rate of change function is that values of the dependent variable are rate of change. So given any value of the independent variable, your corresponding value of the dependent variable is a value of rate of change. Okay? At the instant of the value of the independent, did we get rates of change at an instant? Not quite, right? At an instant, there's no change. You have no change, right? So you can't talk about rate of change without at least a little teeny bit of change. So we're talking about rate of change at, remember what we talked about? At moments, right? So we think of the independent variable as a succession of moments, right? And their dependent variable in a rate of change function would be rate of change. It gives the rate of change at every moment of the independent variable. What's that? What do we mean by rate of change in a moment? Go. What's that? Okay, so the rate of change function, we said values of the dependent variable are rates of change at every moment. What do we mean by rate of change at a moment? What's the key to that? Where's Sean Holland? What's the key to rate of change at a moment? Okay, so we calculate it by the change in accumulation over the change in independent. There's more to say about that, though. What else could we say about rate of change in a moment? This is one of the keys of the whole course. What is a rate of change in a moment? What kind of rate of change is it? Someone said it. Constant rate of change. That's the key. Rate of change in a moment is what? The moment is a small enough interval so that we have essentially constant rate of change. And then we calculate it by change in y, change in accumulation over change in x, or change in y over change in x. Okay? So by rate of change in a moment, we're talking about a constant rate of change that we can get by change in y over change in x. Because it's essentially, we're essentially, the rate is essentially constant for small enough interval, which we call a moment. Okay, so let's look at, got this application here. It says, when the ground fault opens, scientists begin measuring the width of the opening in centimeters at a certain point along the fault. They take regular measurements for several months and model the data with a function W, whose graph is shown below. Okay, and so remember, the way we think about graphs is there was a point in time when these correspondence points came to be in succession, right? They were generated. Time went by, and they took the data, and so that's the way we want to think about a graph. When you see a curve, you think about it as a set of points that were generated continuously as your independent variable increased, right? Okay, so this particular function, is it accumulation? And we could say, is it net accumulation? Is it total accumulation? Is it amount? Or is it rate of change? And what does the point 1.5, 5.225 represent? Go. Okay, where's Fahad? Alabama. Is Fahad here? Not here? Blake. Wickland. Where's Blake? Not here? Where is Ziyu Wang? U. I use U. Is this a accumulation or rate of change graph or function? W. Not sure? Okay. How about Matthew Douglas? Or, sorry, Matthew Duplissa? Yes, sir. Accumulation. You guys agree? Okay. You think it's a rate of change graph? Oh, okay. Right. Okay. So when I verbalized the question, I said accumulation or rate of change. So so now let's be more specific. Is this net accumulation or is it total accumulation, which is the same as amount? Right. Total accumulation and amount would be the same function, just thought about in two different ways. So is this net accumulation or is it total accumulation? I still haven't heard the right answer yet. It could be either. Why could it be either? Net accumulation is a function that measures amount of change. And so that will always start at what value? 0. So if we start at time equals 0, we have 0 accumulation. So in that sense, this could be thought of as a change function. Change of width since it started to open. In that sense, it's a net accumulation. But then that's also the same. It's just what the width is at any value of time. So that's also total accumulation. Doesn't make sense. So whenever you're starting at 0, so yes, so at face value, it's a total width function, total accumulation. But because the fault width starts at a width of 0 at time equals 0, you could also think of this function as how much has the fault width changed since time 0, and that's net accumulation, right? Net accumulation. Okay, and what does the point 1.5, 5.225 represent? Where's Bager? Carabay. What does that point, that ordered pair, 1.5, 5.225 represent? Okay, so what was the 1.5 again? And what is that in this context? So 1.5, what? So the point means that at 1.5 months, the fault width is 5.225 centimeters. At 1.5 months, the fault width is 5.225 centimeters. Okay? The point does not mean the width. It means the simultaneous values of those two variables taken together. Right? So the point, so the width is what? How do we express the width? Oh, didn't want to do that. How do we express the width? Right, and on the graph, what is that? On the graph, on the visual, the displayed graph. Just the y-axis, right? So it'd be that arrow that's up there on the left, up on the axis, right? That's the width. But the point together, the point 1.5, 5.225, is when we take those two values together. It's at 1.5 months, the width is 5.225 centimeters. Okay, going on. Okay, so by observing the graph, describe what the fault width is doing at each given x value. I'm going to put a table up here. So at the values I'm going to give you, is the fault width holding constant, or is it increasing or decreasing? And how is it increasing or decreasing? Slowly, moderately, or quickly. So here's the values for which I want you to analyze. 0.25, 1, 2, 3, 4.1, 6, and 8. And for each of those, you're going to say, what is the fault width doing at this moment in time? At this moment in time, 0.25, 1, etc. Okay, so how about the first one together? At 0.25 months, at the moment, 0.25 months, what is the fault width doing? What would you say? Is it holding constant, increasing, or decreasing? Hopefully we all see that it's increasing. And then how is it increasing? Slowly, moderately, or quickly? What should you look at in this animation to answer that question? No, there's something better in this animation to see better than the steepness. Look at the arrow on the y-axis when x is at 0.25. So we're talking about how the y is changing. Watch, ready? Right now. Slowly, moderately, or quickly? Right, so it's thinking about how the y value is changing, and then that results in an inclination of the graph. So really, how fast it's changing is really about how fast that y value, that arrow is moving. Okay, so at 0.25, you guys said increasing quickly. All right, do the others. Go, do the others. Use the arrow. Look at the arrow, not the inclination of the graph. The inclination of the graph comes last. The arrow is what is determining that. One. All right, where's Yao? Yao. Is he here? Y-A-O? Nope, not here. How about Brandon Sharma? Where's Brandon? Brandon here? How about Catherine Randolph? At 1, increasing moderately. Okay? All right, you guys agree? Yeah. Why don't you go ahead and do 2 as well. What would you say about 2? Holding constant? Holding constant for number 2. Agree? All right, next, Walker. Decreasing slowly. And then 4.1? Holding constant. All right, where's Alejandro? Jans. Yep. So do 6 and 8. And then 8? Same. Okay, so answers may vary. So this is kind of, we're just eyeballing things. So this is what I came up with, all right? This is what I came up with. Increasing quickly, increasing moderately, holding constant, decreasing moderately, holding constant, increasing moderately, and then increasing slowly for those. Is that in the ballpark of what you came up with? Right. Okay. Something like that. Okay. How can we estimate individual rate of change values? So now I want to actually, I want to estimate values of rate of change at these moments. How could we do it? Right. Okay, so I'll pause the thing here. So watch. So say at what? At 1. Come up here at 1. And I'm going to zoom in. Right there. That's what I wanted. Okay, so here we are, right there at 1. Oh, okay. So what am I going to do now? So the 1 is that vertical line that point is at. That's the point 1, comma, whatever the fault width is at 1, W of 1. So now I want to estimate the rate of change. What do I do? What do I do? So it's all about what? Rate of change at a moment, right? So at 1, we're talking about a moment at 1 for which we have what kind of rate of change? Essentially constant rate of change. So, or in other words, it's essentially like linear here. Okay, so maybe, I mean, we're just eyeballing, right? So I could just think about it as straight like this. Try again. I need a different color. One more try. There we go. Something like that, right? And so how would we estimate the rate of change then? Change in y over change in x. So we got to know what our scale is. But it looks, I mean, just as a rough estimate, our change in x would be just one horizontal grid line, and our change in y would be about one vertical grid line, just to get something quick. Okay, so we just figure out we got to go back to the scale and look at what's one horizontal grid line. That's our change in x. What's one vertical grid line? That's the change in y, and that's a decent estimate now here for the rate of change at 1. So let's just do that. So we just got to remember it's just one of each. So the grid lines for x are 0.25 months, and the grid lines for y are half a centimeter. Okay, so every grid line is 0.25 months horizontally between grid lines, and then vertically between grid lines it looks like half a centimeter. So estimate the rate of change at 1 month. Go, estimate the rate of change at 1 month. These are every 2, right? Okay, where's Justin Kim? Or did I just call you? Did I call on Justin Kim already? Sorry. Dakota. What was that? I put a mark there. So, Justin, you're up. Okay, so what did you get for the approximate rate of change at the moment 1 month? 0.25 divided by 0.5. So 1/2. Dakota, so you were next. Do you agree with that? 2, because don't doubt yourself. Don't doubt yourself. Just because he said one thing, go with what you. Because why? Change in y over change in x, right? Change in y is 0.5. That was what I told you one change was. Change in x 0.25. So it should be about 2. All right, about 2. Okay, and so we could do that for all these points. We could zoom in until it's linear, get the change in y, change in x, and this would be estimating those rates of change at those moments. And so for time's sake, we won't do that. Oh shoot. Supposed to have these. Hold on a sec. Didn't write them down. Got them in the video though. Here they are. 4, 2, 0, -1, 0, 2, 1/2. Okay. So what do we say? 4, 2, 0. -1, 0, 2, 1/2. Okay. talk. How does each value relate, each of those values I just wrote down, which would be from zooming in, doing change in y over change in x, how does it relate to the second column? Go. How do those values relate to the second column? All the details, okay? Explain all the details of that, okay? There are a few details. Okay, where's Javier Perez? Yes, sir. Okay. Okay, good. So he's saying when values are higher, things are changing faster. And when values are lower, it's not changing as fast. So we're quantifying rate of changes. So we're quantifying how fast the fault width is changing, right? And that's what rate of change is. Rate of change is quantifying how fast our dependent variable is changing. Okay, there's another detail to this. Where is Ivy? You're up. So what did he leave out? He said if the numbers are bigger, it goes faster. If the numbers are smaller, it's changing slower. So there's one more detail to this. Okay. What else do we have here? Yes, sir. Right. Right. When the value is positive, what? It's increasing. So if it's a high positive number, we're increasing fast. If it's a low positive number, we're increasing slowly. Negatives then tell us that the dependent variable is decreasing, right? So whenever it's negative, our change in the dependent is negative, so our rate of change is negative. Okay. Very good. So what important idea does the whole table represent? So I've built this table here, and that represents a really important idea. What does it represent? Volunteer. What does the whole table, what is that a representation of? Okay, approximate rate of change? At those moments. So that's a representation of? Rate of change function, right? So this table is it's representing or expressing rate of change function, right? The rate function. At different values of time, it's giving us what the value of the rate of change is, and so now we're putting kind of meaning on those values. Okay, so here is the width function. Now I want to find the exact values of rate of change. I don't want to approximate anymore. I want to find exact values of rate of change at these moments. Can you do it? Go. Do it. And then so we can split up the work. So just randomly pick any two moments. So that you don't have to do all 7. If you can do 2 of them, you can do all of them. So just do 2 and then that means you can do it. Okay? Fine. I want to find the exact rate of change at these moments. You're either making progress or you're getting help. Go. Okay, is it working? Is your math working? So this is a huge point right here. So it's like, again, this is pinnacle moment in the course. Like if there were 3 lectures or 3 moments in the course where it's like, okay, if there were just 3 things I want them to take with, they really understand. This would be one of them. Okay, this would be one of them. This table was our approximate is a rate function, and we understood how we got those values of rate of change. Zooming in, looking at rate of change in a moment as essentially a constant rate. And what it reflects how the fault width is changing, whether it's increasing or decreasing. It's a quantified way of saying what the fault width is doing, right? If I've got the fault width function and I want to get exact values of the fault width, so I'm looking now for that dependent variable, but exactly, right? I want to know the rate of change exactly. That's a matter of finding what? Derivative, the rate of change function, right? So when you do a derivative, you get rate of change, you get the rate of change function exactly in closed form. Exactly in closed form. And then what happens? Do you have to zoom in and do this calculation, dy over dx every time? No, you could just put that in GC. So I don't think I have it in the thing. So quickly. Did I do the derivative right? Sure hope so. Oh, there's a 2. Okay. How about that? Those twos go away, right? So it's just going to be 1 over the square root of that interior times the rate of change of the interior, right? So we're good at that now. Okay, so what is this? What would you rather do? Would you rather zoom in at points and find its rate of change manually like that, changing y over changing x each time, or use this? Especially if you put that in GC, all you have to do now is just on a new line type what? W prime of 2. And it just instantly gives it to you. W prime of 4.1. And it instantly gives it to you. Once you define that function, right? Closed form and plus technology means instant results of the values of the dependent variable, right? Instant results. This is what I got. If you're off by a hundredth or a couple hundredths, that's okay, right? So maybe you rounded or I rounded differently, okay? So this should be definitely within 5 100ths or a 10th, okay, of what you got. All right, so how do the exact rates match up with our estimates? Good, right? So increasing quickly, and we estimated 4, or we could have, increasing moderately, holding constant, close to 0, decreasing moderately, etc. Okay, so now we've got exact values, and with the closed form derivative function, we could generate lots more really quickly, right? Advantage of having a closed form function. A formula that just gives us rapid results, right? As opposed to an expression that's reflecting process, right? Like an open form expression reflects process, doesn't give us that ability to crank out answers. And what's an example of an open form expression? Integral, right? An integral function. When we write that net accumulation or total accumulation using an integral, that's an open form expression. Reflects that process of summing up the little bits of change, right? But doesn't give us the rapid results like the closed form could. Okay. Any questions on this? Bringing together all this stuff, the relationship of the derivative to our approximate rates of change, and what they mean in that second column. Any questions? Hopefully this is tying things together really well. Okay. So let's look at, here's the same deal. There's the rate of change function. Here it is being generated again. So now I want you to close your notebook on the values. Don't look at the values. So cover those up, the values that we just found. And now I want to, by looking at the general trend of the fault width accumulation function, can we sketch the whole rate of change function? So I want you to cover up the values because I don't want you to plot points and connect the dots. I want want you to think about things in trends, right? Think about things in trends. So given this accumulation graph, can you just sketch roughly, not with any computation, but can you sketch roughly what the rate of change graph would look like? Go. Here's what it actually is. Here's what it actually is when we let GC do that, plot the actual. So what function is it plotting over there? What function is it plotting? The exact rate of change, or the derivative. That derivative function that you found, now it's plotting that, okay? And so for those moments that we found, the y values at those moments would be, right, would be those rates of change that we found exactly for this graph. Okay, so the next little part of the course, we're going to talk about what the idea of kind of what you just did when you sketched that rate of change function. What were you doing? You were coordinating the values of values of accumulation and how the accumulation is changing, coordinating that with rate of change. Okay, and so there's really just two rules to this. And when things get difficult, say next week, it's going to kind of get complicated, and it's going to seem easy at first, and then all of a sudden it's going to get complicated and we're going to get lost. We go back to these kind of bedrock principles that when the fault width is increasing, what do we know about the rate of change function? It's positive, right? When the fault width is increasing, we got a positive rate of change, which shows up how on the graph over there? How does positive rate of change show up? Above the x-axis, right? When the fault width is decreasing, rate of change is? Value of the rate of change is? Negative, which shows up below the x-axis. Okay? So this is going to, when things start getting a little more tricky, we just have to keep returning to this. When values of a function are increasing, the rate of change is positive. When values of a function are decreasing, the rate of change is negative. Okay? This is kind of our bedrock principle. And everything we do as we're coordinating derivatives and the original function really comes back, 80 to 85% of it is really just this. Remembering and applying this. Okay, so let's practice or start talking about that. So I'll leave that up there. And what I've got over here is this. So we're going to look at this in sections of x values. We're going to start with from -4 to -2.5, and we don't know what the function is. We don't know what the original function is, but I'm going to show you the values of rate of change as x increases. First, I want to turn that one off. Okay, here we go. So you don't know what the function is, and but the information that you do have is going to be as x changes from -4 to -2.5, I'm showing values of rate of change, the r sub f of x. Okay, so imagine those are lowercase x's. Okay, so this is just, what is the value of x? These are lowercase x's, imagine. So what's the value of x? And what's the value of the rate of change at x? So we're thinking about x changing from -4 to -2.5 and looking at values of rate of change. And what can we conclude about the original function based on those values of rate of change? Okay, so just I want you to think and discuss. what can we conclude about the function with this information about the rate of change as x changes from -4 to -2.5? Go. Okay, so in this first section here, rate of change. First of all, what can you say? So there's kind of two things. It is and it gets, right? So what is it? You could say the rate of change is what? Always. Okay, so we don't want to focus on as much on the rate of change decreasing and increasing at this point. We just want to focus more on going back to these statements. So what can we say about the rate of change? It is what? Positive. That's the most important thing we want to look at here. Okay? Yes, it is decreasing. So yes, it's positive and it's decreasing. But for our purposes right now, positive is the important thing. The rate of change is r sub f of x. This is going to be that first row in the table here. Positive. And then, yes, we notice also that it's and decreasing. Or what? Getting less positive. Less positive. Okay? And so what does it mean about f of x? He said f of x is increasing in this whole interval. Agree with that? Yeah. If the rate of change is positive in this whole interval, then that means f of x is increasing. That's what we said above, right? We know if the rate of change is positive, the function is increasing. Why? Because changes in x are resulting in positive changes in y. It's increasing. Final y is greater than initial y. Okay, next. It does get a little bit harder. So we'll go now from negative 2.5 to negative 1. Next segment. Now you're going to look at from negative 2.5 to negative 1, and you're going to ask, what is r sub f? And what about f in that interval from negative 2.5 to negative 1? Go. All right, where's Samuel Culberton? Samuel. So tell me, what did you see? Tell me about what you see the values of the rate function in this interval. Okay. Yep. So they at the beginning they're positive, and then it changes to negative. Okay. And so, and then what? How? And then just and then as a secondary um, observation here, are they getting? They get more or less positive? Less positive, and then more or less negative. So you should be seeing that they get less positive at first, and then more negative. And the conclusion is from that, is it decreasing and then increasing, the rate of change? Is it decreasing the whole time? Is it increasing the whole time? Or is it part of both? Increasing then decreasing? The rate of change? You should see the rate of change is always decreasing. When values get less positive, of course they're decreasing. But here's the thing that's not always clear to students. When values get more negative, that's still decreasing values. When values get more negative. So this is still always decreasing through here. Values are getting less positive and more negative. That's a decreasing rate. That's a decreasing rate. And we'll focus on that later. But the fact that the rate of change is positive and then negative means what about F? Means what about F in this? Where's Zayun Lee? Zayun. Yes, sir. What does it mean, just this part of it? The rate is first positive and then it changes to negative. What does that mean for our function? Increasing at first, and then it's going to change to decreasing, is what he said. Agree? Yep. So when the rate is positive, the function is going to be increasing, and then when it's negative, the function is going to be decreasing. But the rate is decreasing the whole time. It's becoming less positive and then more negative. Doesn't make sense. All right, let's do the next one. Here we go. -1, 2, positive 0.5. So as x changes from -1 to +0.5, what's happening to the rates? And analyze the rate. Go, talk about it. Okay, where is Kamal? Abshir. Kamal here? Not here? Justin Kim again. You're up again. So let's talk about the rate in terms of positive and negative. So in this interval, what about the rate of change? Positive? The rate positive? What do we think? Where's Marvin? Lister? Negative. The whole time, or is it sometimes positive? He said the whole time it's negative. Agree? Yeah, so the rate, first and foremost, through this whole interval, the rate of change is negative. Okay, and so now just as a secondary, the whole time it's negative. And how is it changing? How is the rate changing in this interval? Volunteer, can you describe what's going on? Yeah. He says it goes from decreasing to increasing. Go ahead. Yeah, so yeah, that's it, certainly, and that's only because I'm showing you two decimal places. If I showed you more decimal places, that amount, that moment for which it's holding constant would seem a lot smaller. Okay, so because I'm only showing you two decimal places, it seems to really hold constant for a large interval of x, but that's not really the case because I'm showing you only two decimal places. But but yeah, so it's decreasing. And how is it decreasing? Getting more negative. And then how is it increasing? Getting less negative, right? It's negative the whole time. For negative values to decrease, they get more negative. For negative values to increase, they get less negative. They move back towards zero. All right, what can you say about the function then? Samuel, you're up again. You can be up more than once in the same time. So tell me about the function in this interval if the rate of change is negative. So, which one? I heard a couple different things. Decreasing, right, the function values will be decreasing. Even though the rate is decreasing and then increasing, it's negative the whole time. That means our function is decreasing the whole time for the whole, all those x values. Any questions? Makes sense. All right, last interval. There we go. 0.5, 2, 2. Let me start at the beginning. Go. Analyzing the rate and making conclusions about the function. Analyzing the rate, making conclusions about the function. Okay, there should be a lot more people talking right now. Kathy, you should be talking. Go. Okay, where's Metagamon? Is Metagamon here? Last name Ann? No? How about Anna Gutierrez? Is Anna here? Is Anna Gutierrez here, or did she drop? Okay. How about Juan Cardenas? No Juan? Walker. Again, he's up again. Negative at first, and then he said at about x equals 1, it switches to positive. All right, and then how does it do that? Increasing the whole time. How do negative values increase? By becoming less negative. Good. And then how do positive values increase? More positive. That's easy, right? The positive's easy, right? But it's this negative, it gets a little tricky, right? So negative values increase by becoming less negative. Why is that tricky? Because when you have a less negative rate, what's happening to the quantity? It's changing faster or slower? See, it's changing slower. But because it's a negative rate, changing slower at a negative rate means an increasing rate of change. Preview of things to come. Do you see how that can be confusing? Less negative values mean a higher rate, but it's going to be changing more slowly in the negative direction. See that? Okay, that's why it can get confusing. Okay, and so then if the rate is negative and then positive, keep going. Okay, so now I want you to make a rough sketch of the graph of f. What piece of information is missing here that kind of limits us here? We got the rates. We got all the rates we want. What's that? Yeah, so we don't have any particular value of amount or accumulation. So that means, what do we not know about where this graph is? How high or low it is, right? So we don't have no idea actual values of accumulation, so we don't know where the graph is up or down. But once we have a starting point, say here, just if you have a starting point of accumulation or amount, now we can sketch it, right? Now we can make a sketch, so we'll just call it that. Go, sketch the graph of f from -4 to 2. Okay, where's Christy? Christy Sluter. All right. Sorry, did I say your name right? Okay, good. Tell me, I'm just going to put my pen on here. You tell me how to move it. Okay, but remember, if we're drawing F. Drawing F. And I don't know where it starts, so I just picked here, right? Because we don't have any information about a particular amount of accumulation. We just know how it changes, right, from the rate of change. So I'm going to start here, right? That whole interval, okay. And then start going down here. Okay. Okay. All right, so we're just following what we did. We did all the heavy lifting already. Now we can just sketch it. If we're sketching F, it's going to increase, and then in that second interval, increase and then decrease, decrease, and then decrease, and then increase. Let's actually see it. Had to fudge a little bit there, but yeah. Okay, yeah, so that's the idea, right? So that's the graph you should have sketched. Okay, so now notice, so we really focused on if the rate was positive, it's increasing. Wherever the rate was positive, it's increasing. Wherever the rate was negative, it's decreasing. And so then, yeah, so that's where the accumulation is, increasing, increasing, or decreasing. But now look at this. So now, what about looking at where the rate is decreasing or increasing? What does that tell us about the original function? If the rate is decreasing, looking at the red is function f. What conclusions can we make about f from the fact that the rate is decreasing all through these first two intervals and then changes to increasing over here for the greater x values? So see what you come up with. Talk. So what can we say about the function f now thinking about whether the rate is decreasing or increasing? Not just positive or negative, but decreasing or increasing. Go. Okay, now, is the rate through here, is the rate increasing or decreasing? The rate. So the rate we can visualize by this blue tangent line, right? Decreasing. What about the rate now? Still decreasing. So that the rate of change is, when the rate of change is decreasing, what can we conclude about that red graph? You see all through here, even now, the red graph is doing what? We go left to right. It's like turning or bending down, right? Even on the way up. On the way up, it's turning and bending down. On the way down, it's turning and bending down. That's a decreasing rate of change. Look at the blue line. Decreasing rate of change means that that blue line is turning downward. It's turning down less. The rate is decreasing. And then what happens? Right about here, now the rate of change is increasing, right? So that blue line, how fast the function is changing is increasing, right? So that rate of change is increasing. And so what does the graph do of the function? It turns up. On the way down, it's turning up, and on the way up, it's turning up. So the rate is increasing. So this has to do with what we're going to do next, which is called the second derivative. The derivative of the first derivative tells us how the rate is changing. How fast is the rate of change changing? Happy weekend.